Yes, I'll be talking about remotely sensed rivers. I put remotely here in brackets as this word actually has two meanings. The first is that if we use the first one, we are actually not measuring the rivers at all. And in the second one, we are measuring our rivers from a distance. So I will talk about the second one. So in terms of remote sensing, what is remote sensing and what have we been working with in my PhD? Remote sensing is basically when you measure a system from a distance without actually interacting with the system. So this can be a wide range of different technologies, but in my PhD I have been focusing on a selected few, and these are the satellite images and aerial images. And satellite images are of course collected by the orbiting satellites, which go around the Earth on a daily and weekly basis. And aerial images you can get from either historical databases or usually captured by drones or by aeroplane. And the third technology I've been working with is LiDAR. LiDAR is a laser technology, usually mounted on an airplane. You can have different types of LiDARs. Red LiDAR and green LiDAR are two examples, where the red LiDAR is a land-based survey, and the green LiDAR is a more water-based survey because it's able to penetrate the water surface and thus can give us riverbed topography. And finally, the sonar, which is the same as echo sounding. You need that to kind of supply the other ones. So the idea behind using these technologies is basically to obtain a digital twin of the system. So that's basically the main goal. And in our case, this is mostly a large-scale detailed terrain model. And once we have that in place, we are able to apply this in a range of different areas. We have been focusing mostly on environmental design projects in relation to hydropower, but this also includes hydraulics and hydromorphology, ecology, and a range of other applications. So remote sensing it actually does enable us to obtain large-scale data in both space and time. And I'll describe what I mean by that. For example, if you look at satellites, as I mentioned before, they are circling the Earth or orbiting the Earth on a weekly basis, which means that you can actually get new data every week from these sources. And then you have drones, which has the same principle as satellites. It collects images, basically, or you can actually collect a range of data, but we've been looking at images mainly. But these drones enables you to have a little more local focus in your data collection. And then you have LiDARs, as I mentioned, this laser technology. These will give you a very dense data set, usually point clouds, which you can actually use later. They can be both time and costly due to some elements I will describe later. And then, of course, as I mentioned, sonars or echo sounders, usually equipment mounted on boats, which you can use in the rivers to literally fill in the gaps where the water is too deep or where the image is not good enough. So all these different technologies are being applied for the same target. Basically, we want to measure the riverbed and the terrain and able to use it for other applications. And here in this 4 pictures I've set up, you can see the 4 different technologies I've been mentioning before. So you have up to on the left-hand side, the upper left-hand side, you have the satellites. And then if you go to the right-hand side, you have the aeroplane, which can have a LiDAR or laser mounted to it. It also takes photos. And on the lower left side, you have the drones. And on the lower right side, you have the sonars mounted on a boat. And what you can see in this picture is the green line is land and the blue line is water. So you can see that on the right-hand side, those technologies actually directly penetrates the water surface and gives us direct access to the riverbed topography. While on your left-hand side, you have the satellites and the photos from drones or images from drones. You can see they stop at the water surface. So this adds an extra layer of processing in order to get the riverbed. So we want to obtain this digital twin or digital laboratory. So we actually go from these images, for example, as you see on the left-hand side, and you obtain a certain kind of point cloud, which can be very dense or can be dependent on the quality of the data, or you can obtain pixel-based maps. And finally, you want to transform this into a full terrain model like you see on the right-hand side, which have all this application I was talking about. But the thing is that on the left-hand side, you see an image. And when you use, for example, satellite data, you can get a new image every week, at best, of course. It depends on the quality and time of the year and things like this. But remote sensing enables us to get updated terrain models actually over time, in addition to using different sources for the different levels of quality, as we can see. This is actually a picture from River Nea, close to Trondheim. So you can see it's the same picture and a fully formed terrain model in the end here. So I'll give you 2 short examples from my PhD. In the first example, we have been using remote sensing in River Gudbrandsdalslågen, which is a bit south of Trøndelag, south of Dovre, close to the city of Otta. Here we have accessed several years of fish observations for European grayling, as you see in the picture of the fish here, that's a grayling, and also brown trout. So what we did here, we accessed green LiDAR data from a public website available for all, and also aerial images. And this green LiDAR dataset had some, in the deeper areas, it was, they used sonar from both to fill in the gaps, as I mentioned earlier. So what you see here is, the first one is an aerial image, and the second picture on the lower right is the hydraulic model we've been setting up, and it shows the different velocity patterns as you have in this very complex system. So some results. We tested, or we analyzed hydraulically and spatially the different parts of the river and connected these results to observations of fish. So we had zones where many fish were, and zones where you hardly found any fish, and zones where you didn't find any fish at all. So we analyzed the differences hydraulically and spatially in these different zones. So what we found was that, for example, for grayling, it preferred very high spatial and hydraulic variation, specifically during its spawning period, where it is mating and reproducing. So we found that the highest hydraulic variability was in the areas where we found the most fish, basically. And when I say spatial variations, we did an analysis of the riverbank shape. So the more complex the riverbank shape was, the more likely we were to find fish there, or grayling at least, during spawning. We did the same for trout, brown trout, which also is existing in this river, but we found no significant differences between the different areas or the different complexity in hydraulics and spatial, and sinuosity, as we call it, the riverbank variation. So very clear results on grayling, but not so clear on trout. So this was one of the examples where we have been using remote sensing and connecting it to more the ecology of a river, as an example of that. And in the second example, we use, it's basically a method development where we use remote sensing data to obtain riverbed maps in rivers. Here we have been using green LiDAR and aerial images, and satellite images, and also sonar in this for this study. So we looked at 4 different rivers within the central regions of Norway, and we have a lot of images from satellites, and we have an aerial photos, and we've been analyzing those, connecting or trying to find large-scale depth maps directly from these. So basically, an image has usually 3 different bands, where each band in an image represents a certain part of the light spectrum. And each different band has its own capacity of capturing a terrain. So by using a combination of these different bands in an image, that is in each pixel, you get an X value, and this X value is proven to be in relation to the actual depth of the river. So we used a small portion of the river where we knew the depth, we connected this to X, and then we applied this linear relationship to the whole picture, and then we could get these riverbed maps for many kilometers. And each time you get a new image, you can do this process again. So this is just selected results from River Nea, where you can see the picture on the left-hand side is the aerial image, and on the right-hand side you have the depth model. It's not very clear here, but I've focused some areas where you can see the weirs in Nea. There's a lot of weirs. And you also can see that the island is captured, and you have kind of a quite good depth map just based on images. So finally, a summary. There are many steps. I will not go through this figure, but this is just to show you an overview that there are many steps in the process from getting a remote sensing data to actually obtaining this full depth or riverbed maps. And the maps you obtain are highly dependent on the quality of the source, of course, as in many cases. But a good thing is that many remote sensing data are actually freely available for everyone to use today. I've mentioned some links here. You can get the presentation afterwards, or just ask me and I'll send it to you. But using these sources, you can already today start the process of getting good depth maps for a range of rivers in Norway, for example.